Hello and welcome everyone to the next of our Winter Science Speaker Series talks hosted by the Maria Mitchell Association and featuring former MMA interns. I'm Dr. Regina Jorgensen, the Director of Astronomy here at the MMA, and I'd like to thank you all for tuning in tonight. The MMA is a nonprofit organization dedicated to memorializing the legacy of America's first woman astronomer, Maria Mitchell. And I'd like to start off tonight actually by thanking our sponsors for tonight's event, which include Bank of America, TMT, the 30-meter telescope, the White Elephant, and Cisco Brewers. Please remember to join us this winter every other Wednesday at 7 p.m. here on Zoom to catch other exciting MMA speakers. And before we begin, I'd just like to make one note about how we'll run the program. We're going to hold all questions, although I highly encourage you to ask questions. And if you have any, please use the Q&A function, which you should find somewhere down at the bottom of your screen. And we'll take all the questions at the end. But please do ask questions. We'd like to have this be as interactive as possible. So now it is my really great pleasure to introduce our speaker for tonight, Alexandra Mannings, a former NSF-REU intern from the Maria Mitchell Association, but from back in summer 2018. Alex is from Atlanta, Georgia, and received her undergraduate degree from the University of Alabama. And she's currently a third-year graduate student at the University of California, Santa Cruz, which is actually one of the top astrophysics programs in the country. And for the past several years, Alex has been working on a really exciting field of research that she's going to be talking to us about tonight, involving the follow-up observations of the host galaxies of something called fast radio bursts. So Alex is a member of a collaboration called Fast and Fortunate for FRB Follow-Up, of which the MMA is also a member, and it's really been my great honor and pleasure to continue working with Alex over these several years via this collaboration. But Alex's achievements really go far beyond any single institution or collaboration, and she was recently awarded a prestigious and highly competitive National Science Foundation Graduate Fellowship. Moreover, she also has the distinction of being one of the few graduate students to successfully PI, or which means lead, an observational proposal to the Hubble Space Telescope. And I believe we'll be treated to seeing some of those results of this really amazing work tonight. I'll also mention Alex has many interests that go beyond astronomy and is an accomplished dancer. And in fact, one of my favorite memories of the summer that Alex spent here at the MMA with us was really when she helped to orchestrate and choreograph a truly epic astronomy intern dance performance. I think maybe the first and only time that this has happened in the history of the MMA, to celebrate Maria's birthday on August 1st. And it told the tale of the formation and evolution of the universe, starting with the Big Bang. And it was an interpretive dance done by the interns, and is really one of my favorite memories of being here at Maria Mitchell. So in any case, I really am looking forward to her talk tonight. And I'd just like to say, Alex, thank you so much for being here to share with us tonight all of your exciting research. And I will just say one more time, as I see a couple more people have joined in, I encourage you to ask questions throughout the talk tonight. Please use the Q&A function, and we will get to all of the questions at the end of the talk. And so with that, I'm going to stop screen sharing, and I will turn this over to Alex. Alex, thank you so much for being here tonight. I'm really looking forward to this, and I really appreciate your taking the time to share with everyone all of the super exciting work that you're doing.
Yeah, thank you for having me. I totally forgot about that dance. Oh my gosh, that's really hilarious. That was really fun. Yeah. And my summer at Maria Mitchell was definitely one of the most memorable summers I've ever had. It was so much fun. I learned so much. And yeah, it was a life-changing experience, honestly. So
for us too, we loved having you. It was really fantastic.
Thank you. Okay, I'll start sharing my screen and get right into it. Hello, everyone. Thank you so much for joining this talk virtually. It's nice to see some familiar names. I can't see your faces, but I'm imagining them. Yeah, as Regina said, I'm currently a graduate student at UC Santa Cruz, nearing the end of my third year. And for most of that time, I've spent my time researching fast radio bursts and specifically the host galaxies that they come from. And so today my talk will be focused on using Hubble to investigate the mystery of fast radio bursts. So first I'll start off with story time, the story of the discovery of fast radio bursts. It began in 2001 when a millisecond duration signal was detected as part of pulsar observations. And this is a radio signal only lasting a very, very short amount of time, milliseconds long, coming from an object called a pulsar. These are dead stars that have really strong magnetic fields. And along the poles of those magnetic fields, you have radiation beaming out, and these stars are rotating very quickly. And so you observe the or pulses from this star as it rotates around, and you see the beam and the beam moves away, you see it moves away, that sort of thing. So this signal is buried in some data from 2001. And in 2007, Duncan Lorimer, a professor at West Virginia, and an undergraduate student, David Narkovich, discover this pulse in archival data from 2001. And they were searching through this data, looking for bright, distant pulsars from the Small Magellanic Cloud, which is a dwarf galaxy nearby the Milky Way. And so in this figure down here, you can see that pulse, what it looked like. This kind of broad sweeping white line going across there. And this was a very odd signal. It didn't really look like the other pulsar signals. They didn't look like how they expected it to for a usual pulsar. So here is a quote from a article that Duncan Lorimer and his wife, Maura McLaughlin, wrote for Scientific American that was published in 2018. It reads, Narkovich visually inspected the signals the software detected to weed out the more than 99% that were nothing but noise or human-made interference. The signal he found was perplexing, not only because it was so bright, but because it came from a region of the sky a few degrees to the south of the Small Magellanic Cloud, where we would not expect any pulsars associated with the dwarf galaxy. So they're not expecting to see any pulsars in the part of the sky anyway, and it's super, super bright. Most surprisingly, the signal had a very high DM. DM stands for dispersion measure. And that's just the measure of how much that signal sweeps across here. So the light is traveling through the universe, it's interacting with ionized materials, all of this sort of stuff. And that material acts as a prism that kind of splits the light like this. And so different frequencies of light arrive at the telescope at different times. And so how much that light spreads and the spread over time can give you a sense of how far away the origin of that pulse was. And so this signal had a very high DM, many times higher than we would expect from something in the Milky Way, and 50% higher than expected, even if it were associated with the Small Magellanic Cloud. It suggested, and this is the good part, this is the interesting part, that the source was around 3 billion light years away, well beyond our local group of galaxies. So here is this like anomalous radio flash of light. We don't know what's producing it, but it seems to be astrophysical, and it seems to not be coming from the galaxy itself. So this poses a lot of questions. What the heck is creating this thing? Where is it coming from? Doesn't seem to be associated with a pulsar. What's going on? The mystery begins. So from 2007 to 2012, efforts continue to confirm the observations. And they are trying to find more bursts, trying to find anything that resembles what they deemed the Lorimer burst. Theories abound, doubts rise, spirits fade as they find little to nothing until 2013. A number of bursts are detected with similar properties to those of the Lorimer burst. And this is due to some upgrades that were made to the Parkes telescope, making it a bit more sensitive. And this was fantastic. Finally, this observation, this strange anomalous thing was confirmed. It wasn't noise, it wasn't interference, it wasn't some human-made random thing. This was coming from space. And now even more, a bigger mystery begins. Now we really have to figure out what is creating them. And so many observatories dedicated time to looking for more FRBs. You have the Green Bank Telescope in West Virginia, Arecibo in Puerto Rico, rest in peace, and the Very Large Array, or VLA, in New Mexico. But there was one burst that stood out among the rest that were being discovered around this time. It was first discovered in archival data from Arecibo, a little bit of follow-up from Arecibo as well, and then lots of follow-up time dedicated to the Very Large Array. And that burst is called FRB, Fast Radio Burst, 2012-1102. And this naming convention is the date of detection of the burst. So this is the year 2012, the month 11 or November, and the second day of November. So again, this burst was discovered in archival data from 2012, but it was spotted again in 2015. And from this repetition, they were able to localize the burst in 2015. So new information that we gained from this: one, FRBs can repeat. We didn't know that before. They were just one-off bursts on the sky before this. So now, because of the repetition that this burst was exhibiting, they were able to get high precision localizations for the burst itself. Prior to this, and I'll show a figure of what that may, how they compare in a moment. But before this, localizations were on scales of arc minutes, but now with this burst, they were able to get it down to scales of arc seconds. And this then allows us to study the host galaxies where the burst is coming from. And this can start to answer the question of what is producing the burst, because now we can study the host galaxy, we can study the stars, what kind of stars, how old are they, how massive is the galaxy, is it currently forming stars, all of that sort of stuff. And that can provide really important context to determining what we call a progenitor, or the creation kind of channel, the production pathway of these bursts. So here I'm showing a comparison of what previous localizations looked like to what the more recent localizations look like. So this cyan ellipse that you see is a localization for this FRB 2017-0107. You can ignore these other little circles in there. But within that localization ellipse, there are a number of galaxies that this FRB could be related to. And you can do, you can assign a probabilities, do some statistical sort of tests to guess which one it is most likely associated with, but you can't really make super secure associations between the FRB and a singular galaxy. You can still do some really wonderful science, which was done in this paper, where they were looking at other radio sources in relation to the FRBs, but you can't really do detailed host galaxy studies. However, with the localization that we got for this FRB 2012-1102, The location is denoted by this little star. The localization itself is quite small, so I put the star there so we can really zoom in on it. That star is right on top of a dwarf galaxy right there. And then we can study, now we can really look into the details of what's the mass of the galaxy, where it's coming from. Is it coming from a location where the star formation is a bit higher relative to the rest of the galaxy? In this case, the answer was yes. This FRB was coming from a dwarf galaxy, from a region of elevated star formation rate. And there's also like other radio sources in the host. So we were able to get a lot more information, a lot more context that can inform what theories we think are most likely for the production pathway for this FRB in particular, and then maybe also FRBs more broadly. And more localizations came after this one as well. This FRB is 2018-0916, which was localized to a nearby spiral galaxy. I love seeing pictures of this galaxy. It's so beautiful. The spiral arms are amazing. You'll see another picture of it later on. And here we can see that this FRB is landing kind of on this little faint part of the spiral arm of its host. Even now, we start to see some variation between what different FRB hosts can look like and what that may mean, whether there are multiple production pathways or a singular one that can exist in these different types of galaxies. So the mystery kind of deepens even as we're getting more information. But now we can start to ask more pointed questions. I would want to emphasize that this was a localization of another repeating burst. We still need to localize non-repeating bursts as well. So the one-off singular ones, not ones that are, constantly going. And we want to do this because we want to get all of the information about the, variety of FRBs. We don't want to just focus on repeating bursts because they could very well be created by something different than the non-repeating ones, or we don't want to bias our sample. So we need to localize more non-repeating bursts as well. And there are dedicated surveys that are doing this on a day-to-day basis. One called CHIME, the CHIME FRB experiment that is based in Canada. Another called CRAFT, which uses a telescope called ASCAP that's based in Australia, and another one called MEERTRAP that uses the MEERKAT telescope in South Africa. And for my study, we're using mostly data from the CRAFT survey. They were able to localize a number of FRBs, and then we come in, as Regina mentioned earlier, the F4 collaboration. We go in and we do follow-up. So that means we go and look for host galaxies, take new images to see what we can find at the location of the FRB, and study the host galaxies that we find are associated with those bursts. So I'll do this so we can see better where those FRBs are on the host galaxies. And already we see that we're getting little hints of spiral arms from some of the hosts. Some of them look like maybe they're also dwarf galaxies. And so we're able to now look at the overall properties of these host galaxies. What's their star formation rate, or how many stars are they forming per year? What's their stellar mass? What color are they? All of that sort of stuff. And again, the whole, title of the talk, mystery of the FRBs, what is making them? And studying the host galaxies can start to help us to answer these questions. Many theories include or invoke supernovae or supernova remnants. You might have also heard talk of magnetars being the origin of FRBs, which are these highly magnetized stellar remnants. There were even some thought that they might be caused by compact object mergers, like two black holes merging together or stuff like that. So studying the host galaxies can help us answer these questions. I don't know why that keeps happening. Who did that? So what's missing? There are a few, I guess, other questions that we want to start to ask, which is, what is the local environment like? So right at the point of the FRB, right where we see that black star, there's not much light coming from the galaxy at that point. But we want to study what the light is like there, because we want to know, are there stars forming right there? Are there a bunch of old stars there? And we need a bit deeper or more sensitive imaging in order to start to look at those fainter regions of the galaxy. And that also plays into this next question of, what are the detailed structures of the host? We see hints of spiral arms in this image, but I think we're missing the full extent of what those structures really look like. So again, and also being able to resolve those structures. So having high resolution imaging so that we can really see not only the low surface brightness features, but the details of where these points, begin and end. And also we want to ask the question, is there a faint galaxy at the FRB position that is its true origin? Is there something in the background there that is really the host of the FRB? And we want deep imaging to do that. And that is where Hubble enters the chat. With Hubble, we can achieve those things. We get high resolution, we get deep imaging, we're able to resolve and actually detect low surface brightness features. One example of Hubble really coming in to, I guess, save the day and solve another mystery was with long gamma ray bursts. These are bursts of gamma ray, very high frequency radiation, lasting 2 to about 10,000 seconds. And high resolution, specifically Hubble imaging, was the key to studying these events and understanding their origins. So here are some images of long gamma ray burst host galaxies. We see that they have really wonky structures. They're kind of like these irregular dwarf galaxies. And also since we're able to pinpoint the exact location of the long gamma ray burst in the host galaxy, we can see, as I state here, that they're concentrated in the brightest regions of their hosts. Of course, this study that I took this image from has a much larger sample than just these 4. And we see what I just stated is consistent, that they're concentrated in the brightest regions of their hosts. And that can tell us about whether or not they're in regions of really high star formation or really concentrated stellar mass, like lots of stars are right there. And putting all of these pieces together to form this larger puzzle, we characterized, or they did, characterize the light at the location of the burst, studied other global host properties like the morphology and all of that. They studied the morphologies of the host and compared it to other transients in order to come to the conclusion that the long gamma ray bursts were coming from a special class of supernova. And so all of this was able to be done because of the capabilities of the Hubble Space Telescope. So we have a new mystery now, fast radio bursts. Let's try to apply this same thinking to how we can further investigate the origins of ours. Putting together a high precision localization with high resolution imaging, sensitive imaging, and a decent sample size, we can approach the answers by taking full advantage of Hubble's capabilities. So let's take a closer look at our study. The sample that we chose all had, all of the hosts and FRBs had high precision localizations and a secure host association. So we were very sure that the FRB was indeed coming from the host that we thought it was coming from. 6 of the hosts here were new. 6 of the galaxies had were either published in my paper, or Jay Chititi, another member of our group, published one of them. And then 2 were previously imaged by other people's Hubble programs. The 2 that I mentioned actually earlier, 121102 and 180916. So those together, we have 8 total, which is a pretty good sample size. And here are the Hubble images for all 8. And I just love looking at these so much. Just seeing like this one, the interaction between the 2 galaxies, seeing the spiral structure in some of them looking a little like dwarf galaxies, all this really beautiful to look at. I feel so lucky that I can say I worked with this data. So here's a closer look at one of the hosts. This one was published in Chititi et al., as well as my paper. This is 1906-08. And you can see that in different, these are 2 different filters or 2 different wavelengths of light that the Hubble can detect. So here we're looking at more UV light. We're looking more at star formation and stuff like that. These colors might be a little confusing because the UV is red and the infrared is blue, but I trust that we can make it through and it'll be okay. So in the UV, we see more regions of star formation. So we see these little knots of star formation happening along the spiral arms. And then in the infrared, we can see more of the low surface brightness stuff, the full extent of the galaxy. And now we're looking more at older populations of stars as well in this wavelength. So we can use them to probe different things about the host galaxies. And also, I mean, we've got really great resolution here at the FRB position as well. So we can start to make some sort of inferences about what's happening close to the FRB position itself. So we use this data and we make a few measurements, one of which being the morphology. We kind of quantify what shape the galaxy has, and we can measure its radius. We also look at the radial offset, so the distance from the center of the galaxy to the FRB position. We look at fractional flux, which is, and I'll go through kind of more in detail some of these measurements after this. But the fractional flux is sort of how the brightness of a pixel compares to the rest of the light in the galaxy. So is it brighter relative to the rest of the galaxy? Is it lower relative to the rest? We also look at star formation, stellar mass. We set some luminosity limits on whether or not there may be a background galaxy at the position of the FRB. And we look at the fraction of enclosed light, which I'll explain more. That one's a good one to actually see with your eyes. So first, let's start with the morphology. We use a code called GalFit that helps us fit 2 models to the light in the galaxy. One component is the bulge, which is here in orange. The bulge is just the central, like dense part of the galaxy. And then you have the disk component, which is kind of more broad. And then we subtract these models to see any substructure left over. Do we see little knots or spiral arms kind of sticking out at us after we subtract these like smoother parts away? And then also we're able to derive a half-light radius from this. So here is a residual image of the host. And now you really see the difference between that and then the spiral arms, these dark parts really popping out at you in that residual image. So you use this to get a much better grasp on the structure of these host galaxies. Then we also look at the radial offset. As I said, it's the distance from the center of the galaxy to the position of the FRB. And the value that we quote here is like a weighted average, because you have many pixels that are within the localization. So we take a weighted average. And this is just the projected like angular offset. Then you have the physical offset in kiloparsecs. And then you have a host normalized offset. So this is relative to the size of the galaxy. So the offset is about 1 radius away from the center. Then we also look at fraction of enclosed light. If we're using the infrared image, this kind of gives us a sense of whether or not the placement of the FRBs kind of traces the stellar mass of the host itself. And so we determine a circle that has a radius equal to the offset of the FRB, and we calculate how much light, how much of the galaxy's light is within this little shaded region here. And for this host, 190608, about 80% of the host light is enclosed within that radius. Then we also look at fractional flux. I like to think of fractional flux almost like a testing percentile. Where are the, or how are the pixels testing relative to the brightness of the rest of the galaxy? And so for the infrared inside of the localization, they're about on average testing in the 20th percentile. So not very bright in comparison to the rest of the light of the galaxy. And then in the UV, we're kind of right on top of this star forming knot. So that gives us a little bit of a bump. Now these pixels are testing in about the 40th percentile relative to the rest of the light in the host galaxy. And so this can tell us about, so if it were to be in a really bright region in, let's say, the UV, we said before that the UV traces star formation. So if we're in a brighter UV region, then that implies that we're in a place where a lot of star formation is happening. There's lots of star formation going on. And then that can tell us something about the possible age of the progenitor. Is it a really young hot star that just formed and died really violently in a supernova? Or if it's in a really faint region, now we're getting into the older stars and what sort of older stellar remnant or something could form the FRB. So this is the importance of fractional flux. It is extremely informative. Yeah. So a little recap. We looked at some of these measurements, and through them we were able to characterize the local environment, light and location of the FRBs, and we took a closer look at the host morphology. And we want to characterize the sample and compare to other transient populations. If you think back to those puzzle pieces, we're characterizing the host galaxies and the local environments, but another important part of that puzzle is comparing to other transient populations. And so I'm going to use some words right now that, yeah, but we compute a cumulative distribution function, which we don't really have to remember that or what that is, but that's just one way that we're able to visualize the measurements and then how they compare to one another between different transient classes. And so we compare the FRB's measurements to those of other transients, and we do some statistical tests to try to see if they're coming from different populations. And so we compare against short duration gamma ray bursts. These have origins in compact object mergers. So the merger between two neutron stars or something like this. Long duration gamma ray bursts, which have origins in supernovae. Calcium rich transients, which don't think we know exactly what causes them. They have really high offsets from their host galaxies. Core collapse supernovae, which happen massive star death. Type 1a supernovae, which are associated with white dwarfs, and then superluminous supernovae. So we're going to test the FRBs against these to see if they could possibly be related. And here are just some images of this one is an image, this one is a model of a neutron star merger and a supernova remnant. So let's look at the rest of these chickens. So first, let's take a look at the morphology of the entire sample overall. These are the original Hubble images. And then here are the residuals. So we fit the model, we subtracted it away, and now we're looking at the leftover substructure of the hosts. And we can see that in 5 out of 8 of these hosts, there is apparent spiral structure. And not only that, the FRBs are occurring on or near those spiral arms. And that is a really exciting result because that can really narrow down the sort of age range of possible progenitors. You're looking for something that might have recently been born and died or something like this. We're not looking for objects that are super old. And so it can start to kind of narrow down the theories that are actually applicable, at least to this sample of FRBs. So that was a really exciting result that came out of this. And now we're gonna go over the statistical test that we did for some of the other measurements of the FRBs and these other transient populations. So I'm just going to show a sort of like schematic analogy to what the statistical tests are doing or looking for. On the left, we've got this collection of measurements of these FRB characteristics. And then on the right, you have the characteristics for the other transients. And then you have some area of overlap. And we're going to set a fingerprint threshold. So the size of the fingerprint, if the area of overlap is less than the size of this fingerprint, this is going to stay constant. The size of the fingerprint will stay constant. If the area of overlap is less than that, the samples cannot be from the same population. That's what we're going to say. So now I'm going to sub in the different transient populations for this little gray oval over there, and we're going to see how much they overlap and what that area of overlap looks like in relation to the fingerprint. So let's start with short gamma ray bursts or SGRBs. Here we can already see that this area of overlap does not meet the fingerprint threshold. Doesn't meet the criteria. And a reason for this is that short gamma ray bursts originate in locations of significantly lower brightness than fast radio bursts do. We know that short gamma ray bursts are the result of these compact object mergers, as I said before, two neutron stars crashing into each other. And that happens, that has a really long delay time, and those things happen like way out far away from the galaxy in these low brightness regions. So, okay, we didn't meet that threshold, so now we reject SGRBs and we say, okay, these underlying populations are not similar enough for it to be possible, or probable, rather. Then we compare long gamma ray bursts to FRBs. Again, we don't meet the criteria. That area of overlap is smaller than our fingerprint threshold that we set. And these long gamma ray bursts originate from locations of significantly higher brightness and lower offsets than FRBs do. So LGRBs are more concentrated on the inner parts of their host galaxies and really bright regions. And that does not match with what we know for fast radio bursts thus far. Then we also compare to the calcium-rich transients. This is a little hard to see, but again, we don't reach that fingerprint threshold. It's smaller, and calcium-rich transients occur at higher offsets than FRBs, and so due to that, we reject the calcium-rich transients. And then we get to core collapse supernovae. Here, our criteria is met. We reach that fingerprint threshold. And core collapse supernovae are not rejected during any of the statistical tests. And this is for brightness of the locations where the events are happening, as well as offset and these characteristics. So this doesn't mean that FRBs and core collapse supernovae are definitely related or come from the same underlying population. It doesn't mean that. It just means that we can't rule it out at this moment, at this point. Then we also compare to type 1a supernovae. And here again, we are able to meet that. We do meet that fingerprint threshold. Our area of overlap is greater than or equal to the area of the fingerprint. And this type of supernova is also not rejected during any of the statistical tests. There are similarities between their offsets and similarities between the brightness of the regions where they're coming from. And once again, this doesn't mean that they are definitely coming from the same progenitor or being produced in the same ways. It just means that we can't rule it out as an option. So this is allowing us to place some constraints on the production pathways for FRBs. We're able to kind of whittle away what theories don't quite match, what things don't quite line up, and get a little more specific about what theories we think really do fit a bit better to the population. And then I want to look at this plot too, because one of the big reasons that we wanted to use Hubble was because it let us get a closer look at the very specific region where the FRB came from in its host galaxy. We're able to look at relatively small scales and kind of zoom right in on the FRB location. And we want to look at how the properties in the local environment compare to the properties of the overall host environment. So that's what we're showing in these two plots here. We're comparing a stellar mass surface density across the entire host to a stellar mass surface density just in the local area where the FRB occurred. And if our points trace that one-to-one line, it means that the local values are pretty average. They're pretty comparable to the values of the rest of the host. If they're above this dashed line, it means that the local value is elevated relative to the host value. And if below the line, then the local value is depressed with respect to the rest of the galaxy. But here for stellar mass, we see those points are pretty nicely tracing the one-to-one line. For star formation rate, we know that FRB 121102, that first one that was localized to that dwarf galaxy, is located in a region of higher or elevated star formation relative to the rest of the host. And you can see that point up here. And then also for comparison, we wanted to look at star forming regions in the Milky Way. And that's what these two star points are here. And we see both of those all three of those are pretty high, are much higher than that one-to-one line. But our points for the FRBs, the rest of the FRBs in this sample, are very close to the one-to-one line. And these are just upper limits. So that means that the actual value is somewhere at or below where these points are, the triangular points are. So overall, the locations of the FRBs seem pretty average or pretty similar to the overall host properties. So let's go through some of the key takeaways. When we looked at the morphology, we saw spiral arms, and that was really exciting. And not only did we see spiral arms, we saw that the FRBs were happening on or very near to those structures in the host, which can give us a lot of information about what possible things could be producing the FRBs themselves. In looking at other transient populations, we found that we couldn't really rule out core collapse or type 1a supernovae or some sort of connection between FRBs and these types of transients. Magnetars are a strong contender for being the A progenitor pathway for FRBs. You may have heard things in the news about FRBs being localized to galactic magnetars and things like that. So we also don't rule that out as a possibility. We look at the sort of overall properties of the FRB hosts and find that they are young, many of them are young star-forming galaxies. And then again, the local environment seems pretty average in comparison to the rest of the host as well. So all of this information together, again, putting all those puzzle pieces together in order to try to get a bit closer to cracking the case, solving the mystery of what is causing FRBs. And although we can't really make any claims of, oh, we think it is this from this study, we can really set some strong constraints on what we think it is not, which is, I think, equally important. We need that context in order to ask better questions, ask more pointed questions, and really figure out what it is we're looking for. So here is just some I guess exciting stuff that came out of this paper. Here's the paper here and all of the co-authors on it as well. They were just a fantastic, and still are, I work with all these people still, a really fantastic group of people to work with. And I feel super lucky to have written my first paper with them. And then also because of that spiral arm result, you might have seen a few articles in the news about this study, which was super exciting and a completely surreal experience. Yeah, so this, the first, I guess, 2.5, almost 3 years of my PhD have been very exciting. And I definitely look forward to the rest of it. So with that, I'll end the talk and take any questions.
Oh, yay, that was fantastic. I can hear all of the applause out there in Zoom land. And also hilarious. And I'll just add really quick, since you were just saying it and being a little bit humble, your paper that resulted from the Hubble study that you did resulted in a huge amount of press. There were actually a ton of fantastic press releases and articles in lots of popular outlets. And so it was a really, really big deal. And we're very, 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 very proud to be involved in that. And it was just a fantastic result. So congratulations on that. Let's see, I guess we can now go to questions. So if anybody has any questions, please feel free to pop them into the Q&A. There are a couple already. Oh yeah, I also wanted to say also, I felt like it was aliens throughout your talk. I don't know why I was getting this feeling that it was aliens. I don't know where that was coming from.
I have to thank my friend for this suggestion of this. I'm not funny or creative enough to have done it on my own.
Oh, that was really great. And yeah. And to that point, I'll just add one more comment here on the end, which I think you were saying kind of at the end. I'm going to second this, that even if this study was not able to say definitively what FRB progenitors are, ruling out possible progenitors is a really big deal, because you kind of showed this in one part of your talk. There's 50 to 100 different theories, including the aliens theory.
Yeah.
So there's a lot of work for observers to actually go through that list and rule them out as possibilities. That's a really important way of doing it. So, okay, let's see. So Kaylee is actually wondering, to what extent does the relatively small number of localized FRBs limit your statistical tests?
Yeah, that's a good question. That's definitely, I guess I can show you something as well about that. So here are the actual CDFs that we computed, and you can see the gray shaded region is the error on, or like the 68th or something percentile for each of the CDFs for the FRB CDF. And so within that gray shaded region, there's actually a lot of the other transients distributions like fall within there. And so being able to increase the sample size would definitely help to shrink that shaded region, give a little more like a structure to the CDF as well, make it a bit smoother, so that we can make even stronger claims about what is or what may or may not be associated with FRB or underlying populations connected to one another and stuff. So yeah.
Okay, great. Let's see, the next question is coming from Charles, who's asking, will the James Webb Space Telescope be looking for FRBs?
So it won't be looking for FRBs specifically, but we can definitely use it to do follow-up for the FRBs. I think we've even submitted a proposal or two in order to observe with James Webb. So it could definitely provide a really great resource for doing follow-up and getting similarly really deep, high resolution space-based imaging of the hosts. Yeah.
Yeah, awesome. At this point, it's just the competition for time is really, really tough. So.
Oh, yeah.
Let's see. We have another question actually from Maya, who's wondering, why did FRBs only appear after the year 2000 or so? Had they looked for them earlier?
That is a good question. I'm actually not sure how early the archival data goes that you might possibly find an FRB. I guess that's a good question for Dr. Lorimer. Yeah, but I think either way, since they didn't what am I trying to say? Since they didn't discover it until 2007, and they were mostly only seeing one-off bursts, I think that made it really hard to figure out like where on the sky should we look? What kind of sensitivity do we need to see them, and all that sort of stuff in order to get like real-time observations of the FRBs.
Mhm. Yeah, that makes sense. And certainly FRBs were happening and have probably been happening, forever. I think probably it is a good question. And I think probably I'd add to what you've already said, that oftentimes when doing astronomy, we tend to throw out things that look like noise or something like that. So it could even have been if they were actually detected earlier, people sort of threw it out because it looked like noise or something like that. That could have happened. I don't know.
Yeah.
We have another question from Lisa, who's saying, thank you for this fantastic presentation, and is actually wanting to step just a little bit away from the science and would really enjoy knowing a little bit more about you as a person and as a developing student, and asks if you'll please share a little bit about your path, which led to where you are now. Specifically, at what point in childhood did you start your journey into scientific research, and what initially sparked it? And have your family members shared any stories about when they knew you'd become an impactful research scientist?
Oh. I don't think I really knew that I wanted to be a research scientist until college. I signed up to do this like research experience thing at my undergrad institution, where they try to get freshmen into research as early as possible, have them know what it's like and all that sort of stuff. And I did that as well as an REU the summer after my first year. And I thought, oh, wow, yeah, this is amazing. I really enjoy this. I didn't really know what it meant to do astronomical research. Like, I had seen people, work at a science museum or something like this, or talk to a professor, or knew that that was a thing, but not really what the day-to-day or the details were like. So that, I guess, didn't happen until around college. But before that, I knew that I liked science. I guess generally went to a lot of science camps and things like this. And yeah, and through classes I took at my high school, or my dad was a science teacher, and interacting with him and seeing, how excited he was about stuff. All that, I think, in combination helped kind of support my love for it. Have my family members shared any stories about no, not with me, at least, maybe with other people, and I don't know, but I don't even know what they would say, because I don't even know if there is a particular moment that I would reference and say that was the time, that was it. So I don't know. Yeah.
Well, that's awesome. Thank you for sharing all that, and maybe you'll have that conversation with them now.
Mm-hmm. I know. I think some of them are on here, so put it in the chat.
Yeah. Let's see. We do have a comment just in the chat. There's a lot of amazing thank yous and whatnot. And okay, we have a kind of funny question. PJ is wondering if you do believe in aliens, and if so, what they might look like.
I do believe in aliens. I mean, believe in them, but yes, I feel like it's that they have to exist. Like, there has to be life somewhere else. And what do they look like? I just finished reading this book series called Binti, and in it, they have all these crazy descriptions of like what the aliens look like. Some are like floating squid people, or like squid jellyfish people. There's one like spider person that like doesn't exist. It's like it's weird. So I think maybe my conceptions of what aliens will look like come out of that book at the moment.
Cool. That's what is it called?
Binti, B-I-N-T-I.
B-I-N-T-I. Okay, awesome. Book recommendation for everyone.
Yes.
Great. All right, last call for questions. If anybody has any last questions, go ahead and pop them in the Q&A. And while we're just giving folks one more minute, I'm gonna go ahead and ask my question, which is if you had, well, I actually have two, it's a two-parter, not necessarily related, but I'm curious if you have, from, you know, kind of everything you've been working on and learning and whatnot, do you think that repeaters and non-repeaters come from different progenitors?
Um,
I know this is one of the big questions right now, so I don't mean to like put you on the spot. I'm just curious if you have formed an opinion or if you kind of still are, you know, awaiting more data.
I think like, especially with 121102, like how weird and funky that one is, just as far as like the host characteristics and all that sort of stuff. Like it doesn't seem to fit with what we know about some of the other FRBs and their hosts, that it really does seem like, okay, that is different, and whatever is creating that is different than what is creating some of the other ones. And that could possibly apply to, right, like all repeaters. So yeah, I personally kind of do think that it's probably different things, somehow related, but because it's, right, a very similar signal, but yeah.
Okay, awesome. We have one more question from Edward, who's wondering, do you have any advice for undergrads looking to get into research?
Yeah, I would definitely say reaching out to, but that can be hard. That can be hard, because I was going to say reach out to a professor and like ask them if they need any help or want to work with undergrad or something, but that can be really challenging just because professors can be kind of intimidating, and writing an email to a person you don't know can be very scary. So if there are like school funded or supported programs that allow you to like apply and get paired with someone or something like that, then I would definitely suggest doing that. It kind of takes out the scary part of having to like form the connection on your own necessarily. You have some help in doing that. Or yeah, if there's like a teacher that you really like and whose office hours you've gone to or something, even if you don't like their research, asking them some advice on how to work with someone else, or hey, do you need some extra hands in your lab or something like that. And then definitely applying to summer REU programs. Those are, oh my God, like so fantastic. You get paid, you get to do research, you make friends, like it's a very sweet deal. So I would definitely suggest doing those, and if you can. And there's like a database on the NSF website where you can look through all of them. And there are some that are geared towards like minority students or like women in science or things like that. So then you can find things that maybe fit your needs or your preferences or all that kind of stuff. So yeah.
Awesome. Yeah. And I'll just back that up and say there's also REUs in all different STEM fields. So we here at Mariah Mitchell, of course, have an astronomy based REU, and there's about 20 or 25 around the country. But there are REUs in physics and chemistry and computer science, all the different kind of STEM fields as well. So no matter what your interest, I will back up your suggestion to apply for as many REU opportunities as you can. They're of course very competitive because there's a lot of folks who apply, but if you don't apply, you definitely won't get them. So my advice to folks is always to apply as broadly as you can.
Yeah, and there are also post-baccalaureate programs as well. If you didn't get as much like research experience during undergrad as you maybe wanted to, then there are lots of those programs to apply for. Mariah Mitchell also has one of those. So yeah.
Yeah, exactly. Awesome. Okay, well, we are a bit past the hour now, and I think we've probably answered all the questions. I see lots of thank yous, incredible talk in the chat, and I'm just going to add my own. Thank you so much. This was really fantastic. It was so great to have you here tonight and to see what you've been up to. I really want to thank you for taking the time to share with all of us, and you know, congratulations on everything you've been doing, because this is just absolutely fantastic, and to be, you know, in your 3rd year of graduate school and be so accomplished, it's really, really, really amazing. We're all so proud of you from back here on Nantucket, and it's just really, really great to catch up. So with that, I will, oh yeah, we're getting more comments in saying thank you. I'll just remind everybody who's attended, thank you so much for coming. I think tune in 2 weeks from now for our next Science Speaker Talk, and you can find information and registration links on our website. And I think with that, we will say good night for now. And thank you again. This was fantastic. Thanks so much. Look forward to your next big update.
Thanks.
Good night.